Hello everyone, and thank you for joining today's session on ArcGIS GeoEvent Server, leveraging real-time GIS. My name is Gregory Christakos, and joining me is my colleague RJ Sunderman. We're both product engineers for GeoEvent Server, which will be the topic of our discussion today. We're also joined by Greg Tiemann as our moderator for the Q&A session, which will be following today's presentation. As far as today's agenda goes, we'll be covering the following topics that you see before you. If you are here today for an introduction to GeoEvent Server, this presentation will have a little something for you. If you have a little experience already, though, with GeoEvent, and you want to see what's new at 10.8.1, we are excited to be showing you some of the new enhancements we've made to the user experience. And then, of course, if you're hoping to catch a brief demo of what GeoEvent Server can do and get a deeper dive into how it's configured to do that, we've got something for you as well. We do have a lot to cover in just 45 minutes, so let's dive in. Before we can talk about GeoEvent Server and its real-time capabilities, we first need to understand what is real-time data. And in its simplest form, real-time data is observational data. Traditionally, this is thought of as things that move, whether it be cars, ships, planes, or maybe even storms, just to name a few examples. But increasingly, with the advent of connected devices and the Internet of Things, real-time data can also take the form of data collected from stationary sensors. So some examples of this might be a water meter or a gas gauge, or maybe data from a weather station. But then, of course, real-time data can also come from things that just happen, such as lightning strikes, accidents, traffic alerts, or tweets. All of this is streaming data that we can leverage within GeoEvent Server to perform real-time analytics and notification. To take a step back here, when we look at real-time data and ask, how does this fit within the broader ArcGIS Enterprise system? The answer is found in the 5 key capabilities that GeoEvent Server provides. We'll be spending some time reviewing each of these capabilities in more depth, but the first is ingestion. GeoEvent Server enables the ability to bring in all the different types of real-time data that we just discussed. The second key capability is analytics. So GeoEvent Server can be used to perform real-time analytics and filtering of data. This is, of course, to detect patterns and trends in most situations. This is a little bit different from traditional GIS, where batches of historical data may be processed and analyzed well after the fact to detect past patterns or trends. The third key capability is storage. GeoEvent Server also enables the ability to store high volume and high velocity real-time data, whether it be in a system file, an enterprise geodatabase, the spatiotemporal big data store, and so forth. The fourth key capability is visualization. Simply processing and storing your real-time data doesn't quite tell the whole story. Most oftentimes, we want to be able to visualize this data. GeoEvent Server enables this through the use of different services, such as map services, feature services, and stream services. The last key capability is actuation. Once GeoEvent Server has brought in real-time data, processed it, and then detected patterns or incidents that are unique to us, it can then use this information to adjust the behavior of things in its environment. This is important when it comes to IoT devices, as GeoEvent may be used to facilitate processing messages for those devices to respond to.
Let's delve a little deeper into the key capabilities Greg just introduced. Data ingest is how data from sensors is brought into GeoEvent Server. Out of the box, configurable inputs enable you to connect to virtually any sensor network, commercial, industrial, scientific, municipal, public, or private. If an external web server or web service provides its data through an accessible REST services API, GeoEvent Server can either query to get the data or receive data being pushed to it. If data at REST is not available, you can configure TCP, UDP, or WebSocket connectors to receive or subscribe to receive the data. GeoEvent Server can adapt data from self-describing formats such as JSON, GeoJSON, and XML and ingest the data for processing. It can also be configured to adapt simple delimited text, such as sensor data broadcast as comma delimited values, or read data logged to a system data file. The point is data from virtually any data source can be transmitted and adapted for ingest into GeoEvent Server. Once data has been brought into GeoEvent Server, it is natural that you will want to apply some processing to the data. GeoEvent Server includes over 24 different types of processors, enabling you to design and publish custom data processing workflows. Some processors are used to calculate derivative values or perform pattern matching and string manipulation. Others help you perform extract, transform, and load operations, mapping data from one schema to another. There are processors enabling you to enrich sensor data with information from external sources using attribute or spatial join operations. And a few of the processors act as monitors, watching for conditions of interest and updating the duration from when a condition is observed until it is no longer relevant. Illustrated here is one of our geometric processors, used to create a polygon buffer about an event record's point, line, or polygon geometry. You can also use our GeoEvent Server Java SDK to develop your own custom processors, or for that matter, custom inbound or outbound data connectors. The GeoEvent Server product gallery has pre-compiled samples of processors other teams at Esri have developed, such as a motion calculator, a reverse geocoder, and a track idle detector. Often, the source code for these sample processors and connectors have been open sourced and made available on GitHub. If your team has a Java developer, the implementation samples can be tailored for your specific need or used as a springboard to develop a completely custom processor. GeoEvent Server can also be used to apply real-time filtering to sensor data, discarding data whose attributes do not satisfy a specified threshold or those which do not satisfy a spatial condition. Illustrated here, we see a sample concept of a filter discarding event records which are not either blue or orange. Spatial relationships are evaluated against a set of geofences you register with your GeoEvent server. You can perform a one-time load of geofences using the geometry from feature records you maintain in a geodatabase and expose through a feature service. You can also actively synchronize geofences by configuring GeoEvent Server to periodically poll a feature service for updates, or subscribe to a stream service for feature record broadcasts. Frequently, we think of geofences as areas of interest and want to determine when an asset's point location is inside or outside. Spatial relationships are not limited to point and polygon tests, however. For example, you can register the fixed point locations of critical assets as geofences and use GeoEvent Server to evaluate spatial relationships, such as whether an event record's geometry crosses, contains, intersects, or is disjoint from a specified set of geofences. This enables interesting use cases, such as receiving and processing a projected area of effect for changing weather conditions. You can use GeoEvent Server to perform real-time analysis and determine when required hazardous weather protocols need to be enacted. A third key capability offered by GeoEvent Server is control over how you want to disseminate processed event data. GeoEvent Server does not inherently store data it receives and processes. It is your choice whether you want to persist event data, for example, as feature records in an enterprise geodatabase. Many times users do want to leverage a feature service to either add or update feature records. Data received in real time often arrives at high velocity or as large blocks of data from a sensor network. When your concept of operations exceeds what you can do with a traditional relational database, there are options to use a NoSQL spatial temporal big data store. Greg will be looking at this in just a moment when we talk about data visualization. If you do not want to store data as feature records, you can broadcast data from processed event records using a stream service. Stream services leverage WebSocket technology to broadcast streams of data formatted as feature records. Any solution component downstream from your GeoEvent server can subscribe to the stream service's WebSocket to receive data as it is processed in real time. We don't have time this morning to delve into all of the different options for data output. GeoEvent Server can push data to an external web server's web service or WebSocket, write data out to a system file, broadcast the data via a TCP or UDP WebSocket, or write to an Apache Kafka topic. There are also options for notification, but now I'm stealing some of Greg's thunder, so I'll yield and let him talk about those capabilities.
Thanks, RJ. The fourth key capability of GeoEvent Server is the visualization of processed real-time data. Like storage, visualizing real-time data is entirely optional when working with GeoEvent Server. In fact, there may be times where the data you bring into GeoEvent does not have a spatial component to it whatsoever. But where there is a spatial component, GeoEvent Server can be used to facilitate sending this data to a variety of different services. All of these different service types can then be consumed in client-side web applications, such as a web map or an operations dashboard, to then display the features. In the example you see here, a simple feature service has been used to display the real-time location and attribute data of buoys as feature records in a web map. This process data, of course, is stored in an enterprise geodatabase. In certain scenarios, though, it can become quite difficult to distinguish discrete features when they start to accumulate in the thousands or millions on the web map. And so one of the key benefits behind using map and feature services with the spatiotemporal big data store is the unique aggregation capabilities that come along with it. By specifying a feature threshold, we can control when discrete features begin to automatically aggregate and render as bins. These bins can either indicate a simple observational count, or they can be configured to display some sort of statistic such as average temperature recorded in an area. It's important to note that as we zoom back into an area of interest, big data feature services support rendering discrete features that fall below that threshold we've specified. Stream layers are another way of visualizing real-time data from GeoEvent Server. Using WebSockets, streaming data can be broadcasted from GeoEvent Server directly to the client consuming the stream layer. It's actually the web client that can then be used to uniquely display streaming data. For example, in the web map shown before you, the stream layer is used to display unique feature renderings for each aircraft. Each aircraft is essentially symbolized with a different color. The aircraft are also shown heading in a certain direction. This is made possible in the client by specifying a heading value for each feature. This is obtained as a part of the streaming dataset. And we'll see more of this in the demo later, but stream layers can also be used to render breadcrumbs for displaying historical tracks. The fifth and final key capability of ArcGIS GeoEvent Server is actuation. So GeoEvent Server offers several methods for actuation. Two popular ones are sending an email or a text message. And we can see in the example before us that as soon as this monitored vehicle leaves the geofenced area, an email is generated notifying a supervisor of the event. GeoEvent Server supports HTML code for formatting notifications as rich text, email, or SMS text messages. With this, it's possible to invoke values from the source event data for the message. This is how, for example, we see driver 1 is headed southwest at 55 miles per hour instead of a more generic message which might be crafted as the driver is outside the zone. We often think of notifications as something such as an email or text message sent to a person, but GeoEvent Server can also be used to facilitate change on network-connected devices. In the example that we see here, different types of processed event data can be used to trigger a response on the corresponding device in the cloud. GeoEvent, for example, may facilitate these types of messages as part of an HTTP POST REST request. But now that we've had a more in-depth look at the key capabilities of GeoEvent Server, I'm going to hand things back to RJ, where we'll take a closer look at how these concepts are realized through GeoEvent services.
Thanks, Greg. Let's switch now and take a look at some improvements made to the design and publication of GeoEvent services. Before we get started with discussing the critical components of a GeoEvent service, let's describe the essential pieces of a GeoEvent service. In its simplest form, a GeoEvent service is what allows you to define the flow of real-time data, or GeoEvents, from an input to an output. At a minimum, a GeoEvent service must have at least one input and one output connector. Adding processors and filters to a GeoEvent service is optional. Processors are generally used to perform some operation on an event record, calculate a value, create a buffer, enrich the event record, etc. Filters are generally used to test attribute and/or spatial conditions and discard event records which do not satisfy the specified criteria. Often, when configuring inputs, outputs, processors, and filters, you need support from other critical elements, such as GeoEvent definitions, geofences you've registered with the GeoEvent server, or server connections you've registered to an ArcGIS server or ArcGIS Enterprise portal. Let's take a look at how these elements are accessed and configured in the Service Designer.
Thanks, RJ. To get started with GeoEvent Server, you'll first want to launch the GeoEvent Manager web application seen before you. While on the home page of this web application, you can click Add Service to begin designing a new GeoEvent service. Simply provide a name for your GeoEvent service and an optional description. For the purposes of this demonstration, I'm choosing to call my GeoEvent service Sample GeoEvent Service. Clicking Create takes you to the Service Designer. From here, you can add the required input and output to your GeoEvent service. Anytime you create a GeoEvent service, at a minimum you need one input and one output connector. However, should you choose to do so, you can certainly add more. Notice here, though, that I do not have any pre-existing inputs or outputs created. Starting at 10.8.1, I can simply create them here in the Service Designer to help keep my focus on what I'm doing, and that is designing and publishing a GeoEvent service. By clicking on Input beneath the New Elements grouping, I can drag to add a new input to my GeoEvent service. Once I do this, I'm presented with a panel which allows me to review all the different types of inbound connectors that are available. For example, I might want to pull an external web server for JSON data that I know is periodically updated. For this, I can configure a pull an external website for JSON input connector. Or let's say instead I want to pull a feature service from my ArcGIS Online organization for feature records. I can simply configure a pull an ArcGIS server for features input connector as well. But regardless of what I choose, I can list all the available inputs by either how the data is being conveyed to GeoEvent Server, for example looking at transports, or switch to look at all the available inputs by how the data I expect to receive might be formatted. And this is, for example, by looking at adapters. The same thing goes for output connectors, though. Clicking Output, I can drag to add a new output connector to my GeoEvent service. Again, I'm presented with a panel which allows me to review all the different types of outbound connectors and sort them either by their transport or their adapter. If I want to add my processed events as feature records to a feature service, I can easily create and add a feature service output connector. Or let's say instead I want to notify someone of a unique event. I might choose to create a send an email output connector as well. For the purposes of this demo, let's suppose I've configured a new input and a couple of new outputs. Returning to the New Elements grouping, I can click and drag to add a new processor to my GeoEvent service. A pull-down lists the different types of processors that are available out of the box. Selecting any processor will reveal pertinent settings for configuration. I can also click and drag to add a new filter to my GeoEvent service. A filter can be configured to evaluate whether the value of an event records field or its geometry meets some sort of attribute or spatial condition. Records that do not meet the specified condition, as configured here, are dropped from processing. In the interest of time, suppose that I have configured a couple new processors and a couple of new filters. Hovering near the edge of any node allows me to click and drag a connecting line to define how event records should flow. Once we connect all these components of our GeoEvent service together, we can then publish and start our GeoEvent service. Now, before we take this step, it is important to note that the successful operation of a GeoEvent service can often mean first making adjustments to different site settings. This is why at 10.8.1 we introduced the ability to access and edit these site settings from here inside the Service Designer. For example, if I need to review my GeoEvent definitions to perhaps adjust the schema of my processed event records, I can simply click on the GeoEvent definitions shortcut under the Site Settings group. From here, I can make all the necessary edits I need to, and even create, import, or delete definitions as well. If I need to, I can also access my geofence settings to manage, import, or delete my geofences. Geofences are often used in spatial filters, and a small handful of processors such as the geotagger or incident detector processor. Now, let's say I'm interested in configuring my GeoEvent service to pull feature records from a feature service. Or perhaps I want my GeoEvent service to instead write processed event data as JSON to a local system file. To make this happen, I would first need to ensure that my GeoEvent server has access to the server either hosting the feature service, or that it can find the local system path to create and write the JSON to a file. By clicking on the Data Stores tab, I can review and manage these types of necessary connections. Here, you see I have my default ArcGIS server connection, but I could just as easily make a new connection to a separate ArcGIS server an enterprise portal, or an ArcGIS Online organization. The same goes for registering local system folder paths. Lastly, if I know I have high volume and high velocity data that I want to store in the spatiotemporal big data store, I can access and manage this content using the spatiotemporal big data store shortcut as seen here. At this point, our GeoEvent service is ready to be started. By default, all input and output connectors are in a stop state when they're first created. However, you can easily start them by right-clicking and choosing Start Input or Start Output. As I do this, you'll notice that there's a status indicator in the bottom right-hand corner. This briefly displays to let me know that an action I took was successful. If there were to be any warnings or errors, this information would display here as well. But now that my GeoEvent service is running, each connecting line between two nodes can be considered a pipe through which event records are flowing. At the bottom of the screen, I can click to expand a utility called the GeoEvent Sampler. Clicking to enable the sampler, I can select any of the connecting lines to see a sample of real-time event records flowing through the pipe. This information is presented to me as a scrollable list in the sampler along the bottom of the screen. In this particular case, I can review a sample of the latest event records routed from the input to the first processor in the GeoEvent service. Clicking on a different line, I now have a sample of event records flowing from the first processor to the first of my two filters. At this point, you may have noticed that on the top of the service designer, we have some status information about our GeoEvent service. Among many things, we can see here that our input count is increasing, but our output is not. This means that somewhere in the GeoEvent service, event records are not making their way to the outputs. But using the sampler, we can begin to explore the pipes of our GeoEvent service to see what is amiss. When the connecting line between the second filter and processor is selected, we see that we have a problem. The sampler displays an indicator that a process is running, but that no data is being displayed. Clicking on the route going into the filter, we can see that event records are making their way to the filter, but the speed of each event record seems to hold a null value. Now, it's important to note that each filter has been configured to process event records if the vessel speed is either stationary with a value of 0, or if it's in motion, meaning its speed value is greater than 0. Because each event record speed appears to be null though, we can deduce that nothing will ever pass through either of the two filter conditions. At this point, we need to determine why our speed is null. Let's take a look at the processor preceding the filters. When I double-click to check the configuration of the processor, I see that a source field has been left unmapped to my new speed field. This essentially means that I'm mistakenly passing null values as my speed. Correcting the processor's configuration, I can now click Publish to commit the changes to my service. I can then refresh the GeoEvent sampler and confirm that my speed is no longer null. Now, when I select the route coming out of the filter, I can see event records are being processed and displayed in the sampler. Likewise, on the top of the window, I can now see that my output count is increasing as well. One thing to note is that you can also use the GeoEvent Sampler to compare event records from two different routes. If I select the route coming from my input, and then right-click and select the route coming from my first processor to compare, you'll notice that the GeoEvent Sampler now displays a split view. On the left, I can review samples of my data as it's going into the first processor, and compare that to the same data on the right that has been presumably changed and is coming out of the same processor. This type of comparison sampling is highly useful for ensuring that my data is changing in the ways that I expect it to. Just to name a few examples, I can use the sampler to confirm that my data's schema, attribute values, or even event record geometry is being processed as expected. Since I've had that sampler open, I have left all the default settings in place. However, I can quickly change these on the fly. If I want my samples to display as delimited text rather than as JSON objects, I can modify this in the sampler settings as you see here. Likewise, if I want to obtain 100 samples at a time instead of 10, which is the default, I can change the sample size as well. Simply refreshing the sampler allows me to get a new batch of records to review with the new settings applied. These settings are persisted for as long as I'm in this service designer view. For now, I'm going to change the data type back to JSON. I want to do this so that I can also visualize the geometry of my sampled events. Visualizing records can be done using a specific feature of the sampler called the event viewer. So let's sample more event records to see this in action. As data comes in, you'll notice that a map icon has become available. Clicking on it will open up the event viewer, which is a lightweight embedded web map application that allows me to display the geometry of my sampled events. You can see, in this case, all point locations of my tracked vessels. Now, just to take things one step further, let's say I want to verify that my point geometry is being correctly transformed into rangefan polygons by my rangefan calculator processor on the right. I can continue to sample the first route going into the rangefan calculator and comparison sample the route coming from the same processor. Here I can see I have more sampled events coming through. If I wanted to verify the geometry, I could simply review the geometry object before and after the processor. Or in other words, on the left I have my points as indicated by the X and Y values. In the comparison window on the right, I can see that my geometry is being handled differently though, as a polygon, and this is indicated to me by the array of rings. Now, while this sort of comparison is useful, I still want to see what these event records actually look like in comparison to one another. If I click on the event viewer once more, I'm now presented with. On the left, I have my original point geometry indicating my vessel's position, and on the right, I have the new polygon geometry that indicates my vessel's line of sight as rangefans. I can increase the scale of both web maps to better explore the detail of my event records, such as in the case of the polygon, and zoom around as well. If there's a particular event that I'm interested in, I can click on it and confirm the appropriate attributes in this pop-up. There's also a locking feature, which allows me to pan around both maps at once if there's a specific event that I choose to seek out. And last but not least, I can change the base map of each web map to something other than the gray default that you see here. If none of the available web maps are suitable for use, or if I happen to be in an offline environment, I can use my own custom web map for the event viewer.
Greg's demonstration of the GeoEvent Server's service designer has given us a good idea of what a GeoEvent service is and how an analyst would use the service designer to design and publish a GeoEvent service. He also demonstrated some of the improvements we've made to streamline common user workflows, such as access to GeoEvent definitions, the ability to import geofences, and review server connections registered with the GeoEvent server, all from within the service designer. For the last part of our workshop today, I'd like to walk you through the actual design of a GeoEvent service. In the past, we've created a final solution, demonstrated what GeoEvent Server was doing by looking at results on a web map, then returned to the service designer Greg just showed to review how the filters and processors were configured to create the solution. Today I'd like to try something a little different. I'll present a scenario or need and start looking at different ways a GeoEvent service might be configured to achieve what we've been asked to do. As we iterate over possible approaches, you no doubt will have thoughts of your own about how to approach the problem, and that's great. Solution design is often iterative as we try different approaches, find limitations, and work around them to improve the solution. Suppose you had a vehicle telemetry feed for a small fleet of delivery trucks. This is not a large-scale commercial scenario with hundreds or thousands of vehicles. Illustrated here are a half dozen stores. The operational concept is that a few trucks are moving inventory daily between stores in response to business needs. A production solution would probably integrate with an actual vehicle telemetry feed using a REST API. It does not really matter, though, how data is ingested and adapted to create event records for processing. So we can begin our GeoEvent service design using a simulation file we're able to mock up in a text editor. We can work out the details for how to get real data into GeoEvent Server later in the project, once we find a viable approach for data processing and dissemination. The only data we need from the vehicle telemetry feed to begin designing a solution is a unique identifier for each vehicle, a date time associated with each observation, and a point location, or latitude and longitude. A commercial vehicle telemetry feed will probably have other information available, but we will suppose that none of it will play heavily into our initial efforts to prototype a solution. We are really only looking for two things. We want to be able to see the last reported position of the vehicles on a web map, and it would be nice to have some sort of breadcrumb trail to give context as to what direction a vehicle is heading. The other ask is that we automate alerting so that a receiving manager on site at each store can receive a text or email alert when an inbound delivery truck is approximately 15 minutes from arrival, so the receiving area can be made ready. The first objective is easily met using a stream service output. If we create a GeoEvent definition with the event record attributes and vehicle geometry we want to display on the web map, we can use GeoEvent Manager to publish a new stream service, then configure a field mapper to map the data schema we receive and copy specific attribute values into the data structure expected by the stream service. With data being broadcast as it arrives, we can add a stream layer to a web map and configure the web maps layer to display the desired breadcrumb trail. All we're looking for here is dots on a map. The second ask is what I would like to focus on. There are several different ways we might think about processing the event data to produce alerts. If we were to import the point geometry modeling the half-dozen store locations into GeoEvent Server as geofences, we could use filtering to determine if or when a vehicle's location intersects a store's location. If we assume that a vehicle in normal traffic approaching a store can travel 8 to 10 miles in about 15 minutes, we might use GeoEvent Server to create a buffer around each vehicle's position as the last known positions are received. When this buffer intersects a store's point location, we can use the truck's track ID to look up which store the truck is supposed to be driving to, get contact information for the receiving manager at that store, and send an email or SMS text. Illustrated here, you see this initial approach uses a buffer creator with a fixed buffer distance, a filter to determine if the created buffer intersects one of the point geometries in our store's geofence category, and a field enricher, which will use either a feature service or standalone table to retrieve information on where a truck is heading and who to contact before arriving. There are a couple of problems with this approach, though. First, a delivery truck passing closely enough to any store will trigger an alert message, even if the truck is not scheduled to actually drive to that particular store. Second, if we create polygons around the reported truck positions, we are limited in the spatial relationships we can test. The geofence geometries must be on the right-hand side of the expression, so to speak, and since a polygon cannot enter a point, we can only really test for geometric intersection. That would mean that as updated locations are received, as a truck drives near the store it is scheduled to visit, duplicate alerts will likely be produced, one every couple of minutes if that is the frequency at which vehicle locations are reported. A geotagger processor could be used to get the name of a store a delivery truck happens to be nearby. A geotagger is configured using the same type of filter expression as the filter we thought to use at first, so we might replace the filter with a geotagger. The lookup table with each day's delivery schedule might not be the same table used to look up contact information for the receiving manager at a particular store. We might handle this on the database side with a table join, but for now let's assume that we've discovered that we need to enrich vehicle location event records twice, once to get the specific store they were scheduled to drive to, and once to get an email address or mobile number for the receiving manager at that store. Given the name of the store the truck is supposed to visit, we can perform a string compare to determine if a nearby store discovered by the geotagger happens to be our final destination. If the strings match, then we send an alert that the truck is approaching and will arrive shortly. This approach isn't terribly efficient, though. We only care about the name of a store a truck is nearby if it happens to be the store the truck is scheduled to visit. Otherwise, the enrichment is intermediate data we will probably end up discarding. If we slide the first field enricher to the left and get rid of the geotagger, we can configure the filter to once again evaluate a spatial condition rather than simply comparing two strings. Notice that the filter's expression has gotten more specific, though. Rather than considering any point geofence in the store's collection or category, The filter uses variable expression syntax to only consider the specific store a vehicle will actually visit. This solution approach is better. We have solved the problem of alerting stores which happen to be nearby but not on a truck's assigned route. But we still have not addressed the problem of duplicate notifications as a truck approaches its destination. We might consider incorporating an event volume control processor in our processing workflow to tackle this. The event volume control processor was designed to cache information such as the track ID of event records it has received. The processor is configured to discard an unwanted volume of event records by allowing through only so many event records for a given track ID every so many seconds. This approach will require that you make some assumptions. We've assumed that trucks will travel the extent of the 8-mile buffer in 15 minutes, so we could assume that sending at most one notification every 30 minutes will allow the first intersecting event to produce the desired alert when the truck first intersects the store it plans to visit. The update frequency of the telemetry feed wouldn't matter, as intersecting events after the first are being discarded. But this feels a little sloppy. The 8-mile buffer might not accurately model a 15-minute drive time if a store is close to a freeway exit, for example. And if we further assume that simply doubling that arrival time window will successfully discard unwanted event records, we may end up discovering that location telemetry continues to be collected as a vehicle is parked in the receiving bay while it is unloaded. The receiving manager could start getting alerts about a truck sitting in his driveway if we keep this approach. Considering our area of operations, we can easily see that the drive time between any two stores is at least a couple of hours, with some hops requiring more like 5 hours. We don't really need to compute a fixed distance buffer around every reported truck location, especially if the only location reports we would really use would be the few dozen at the very end of a truck's route. If vehicle telemetry is being received every couple of minutes, that's a lot of unnecessary on-the-fly geometry calculation. That is exactly the sort of processing costs we want to work to eliminate if our prototype is eventually going to scale beyond a half-dozen delivery trucks and stores. Suppose that we were to create a hosted feature layer in ArcGIS Online and add the point locations of our stores. We could then use one of its proximity geoprocessing tools to create an average drive time area polygon around each store, which more accurately models a 15-minute approach for a truck. The proximity analysis would include street networks and average traffic at a specified time of day. Using GeoEvent Manager, we could then register a server connection to our ArcGIS Online organization to complement the default server connection to the local on-premise ArcGIS server. This would allow us to import the constructed drive time polygons from the hosted feature layer rather than modeling geofences using the point location of stores. This does offer another opportunity for optimization. The drive time polygon illustrated here is much too complex for use by GeoEvent Server if dozens or hundreds of geofences were to be imported at this level of detail. Keep in mind that solutions will need to be able to process hundreds, possibly thousands of event records per second. It would be best to sketch an approximate convex hull around the detailed polygon and use that instead. Trucks in our solution are going to use major highways as often as possible, and will only use local streets as they approach a store, so the high level of detail produced by the proximity analysis geoprocessing tool is not really necessary in our scenario. A polygon like the one illustrated here has about a dozen vertices. In terms of the number of vertices, its geometry is simpler than either the 8-mile circular buffer we had been constructing, or the detailed 15-minute drive time analysis produced by the geoprocessing tool. Yet it should be more than accurate enough for the automated alerting we want our GeoEvent service to produce. Looking back at our GeoEvent service, we want to remove the buffer creator processor and slide the field enricher up so that we enrich vehicle telemetry with the destination store as early as possible. Then we can configure the filter to look at a collection of polygon geofences in a drive time category rather than point geofences in the stores category. Notice that we still name the approximate drive time polygonal geofences with the unique name of the store they surround. This makes the spatial filtering as specific as possible and avoids false alerting if a truck happens to drive past a store it will not be stopping at. Also, Now that we are comparing a truck's location point to an approximate drive time area, we can configure the filter to evaluate an enter condition rather than using intersects, which eliminates the need for the event volume controller. To quickly review what we've covered, today's workshop had three main parts. We started with an explanation of what we mean when we talk about real-time data. We also discussed the role GeoEvent Server plays in the overall ArcGIS Enterprise and reviewed its key capabilities. GeoEvent Server is the server role you add to your ArcGIS Enterprise to unlock the ability to ingest and adapt data from real-time data feeds. The event records created by an input are routed through a GeoEvent service, whose filters and processors apply discrete, specific tasks as part of configurable analysis and pattern recognition. Dissemination of processed event records includes the storage of data as feature records in an enterprise geodatabase, the visualization of this data using feature and stream layers in a web map or operations dashboard, and potentially device activation and configuration. We also shared a demonstration of GeoEvent Server's Service Designer, highlighting common user workflows and recent improvements. The demonstration showed how inputs, outputs, processors, and filters are created, added to a GeoEvent service, and connected to configure an event processing workflow. Some key points to take away from the demonstration are how GeoEvent Sampler is used to inspect data received and adapted to create event records. You are able to sample event records routed to a processor and compare them against event records emitted from the processor to see changes made to the data. The sampler can help you identify changes you need to make to your event processing workflow and service configuration. Finally, we walk through a development scenario highlighting different approaches you can take to configure a GeoEvent service to meet the needs of a specific scenario. This third part of our workshop did not use the Service Designer to edit any of the filters or processors to reveal their configuration, but if you reach out to me, I can provide you with a write-up which shows how the different elements were configured. Here are some resources for self-study and additional learning. Technical workshops Greg and I presented at the Developer Summit and the International Users Conference last year are available online. Last year's technical workshop includes a different case study and demonstration with more detail on how different processors in the solution were actually configured. We continue to add new content to our online help documentation. A significant build-out was completed late last year for the 10.8.1 release. New content was added for inbound and outbound connectors, processors, as well as information on deployment considerations. Esri also released a brand new GeoNet platform to support our community forum last fall. The short link shown here will take you directly to the product area for GeoEvent Server, with boards for blogs, discussion, questions, and ideas for future enhancements. Finally, the Esri Training Catalog has a number of resources. There's a one-day instructor-led course providing students with hands-on exercises and opportunities to work with a certified instructor. If you're looking to get started with GeoEvent Server and would like to talk about training or professional services jumpstart activities, please reach out to us. Here's a quick look at some of the other sessions being offered at the Developer Summit this year. Later this afternoon, Greg and Suzanne will be presenting an introduction to ArcGIS Velocity. Tomorrow, there are two technical workshops with live Q&A. A GeoEvent Server presentation Eric Ironside and I present in the morning will take a look at what's new in the 10.9 release. Then later in the afternoon, Ken and Peter from the ArcGIS Velocity team will present a workshop on real-time and big data analytics. There are also two on-demand presentations. The first is an overview of real-time capabilities across ArcGIS, and the second is a workshop on creating custom connectors and processors for the GeoEvent Server using its Java SDK. Please note that scheduled workshops will include a video presentation with a live Q&A. The scheduled times are all Pacific Daylight Time. If you miss one of the scheduled SimuLive presentations, a recording should be available in a few weeks. Workshops being offered on demand are available anytime, but will not have a live Q&A. That concludes our presentation for today. Again, my name is RJ Sunderman, and with me is Greg Christakos. With that, I'll hand over control to our moderator, Greg Tiemann, so we can get the Q&A started.
Great. Thanks everyone for joining us today to learn about GeoEvent Server and how to leverage the real-time capabilities of ArcGIS. So we're going to start this Q&A today. I have Gregory Christakos and RJ Sunderman, the two presenters for this session here with us today, and I am your moderator. So let's go ahead and get started with the top voted question of the session. Is the intent for ArcGIS Velocity to have the same capabilities as GeoEvent Server? How do the two differ beyond where they run? Will Esri maintain feature parity between GeoEvent Server and the new Velocity SaaS offering? So I'll hand that one to you, Gregory, to answer.
Sure. Great question, Nick. So the intent between ArcGIS Velocity and GeoEvent Server, the intent is to maintain similar feature parity when it comes to real-time processing and those sorts of real-time capabilities. There will be minor differences in processors and tools between ArcGIS Velocity and GeoEvent Server. But aside from where it's run as a SaaS or something that's run on premise, Velocity does offer additional capabilities beyond what GeoEvent Server includes, such as big data analytic capabilities. So if you're interested in learning a little bit more about ArcGIS Velocity, especially now that you've seen a little bit about GeoEvent, there will be a session later on today where we go into the introduction of ArcGIS Velocity and kind of dive into that topic a little bit more.
Thanks, Greg. So next question from Anonymous. How well do related tables work with this, especially when the live data is a table related to a static point map service? Will the static points show the new related table data? RJ, I'm going to hand that one to you to answer.
Sure. So the way I would answer that would be to determine whether I want to use a streaming output, like a stream service going to a stream layer, or if I want to update feature records in a feature service. The feature service will accept a subset of the JSON data structure. So if you had a fixed set of sensors that weren't moving and you only wanted to update their metrics, you would construct or configure a GeoEvent definition that only had those metrics and send just the data to the feature service that you wanted the feature service to update. Then it wouldn't be changing the geometry. It would just be updating the real-time metrics, and you would view it using a normal feature layer on the web map. The stream service is a little bit different in that it will support attribute-only non-spatial streaming data, and you have a capability called related features that will actually do a join on the client side to bring the geometry into the real-time data table, if you will, and then display it as a stream layer. So you have a couple of options there.
Great, thanks, RJ. Next question, what's new in the upcoming 10.9 release of GeoEvent Server? RJ, you want to take that one?
You said what's new in the upcoming release of 10.9. I would ask that we maybe defer this question. We can come over to the island and talk. There is a technical workshop tomorrow that Eric Ironside and I are presenting at, I believe, 10:30 Pacific time that has a lot of demonstration on what's new at 10.9.
Great, thank you. So next question, I've not been able to find a detailed tutorial guide on how to successfully set up GeoEvent Server for a client. I'd really appreciate information about the type of tracking devices I can acquire, how to configure GeoEvent Server, track live locations of devices, and access options such as geofencing. Gregory, you want to talk about some of the resources we have available?
Sure. That's a good question. So as far as the resources available for GeoEvent Server, we do have recently updated online documentation about how to get started with GeoEvent, as well as like an implementation guide that's been revamped. You'll also find on our GeoEvent gallery some GeoEvent Server tutorials where we touch on topics such as geofencing, which was brought up in that question, as well as how to get started. If you're looking for like a comprehensive review or kind of insight into like what sort of applications or devices can kind of interface with GeoEvent on an input or output level, that's something we would probably need to have a more specific conversation about. So if you wanted to come over to the expo, ask the experts, we're happy to talk about that a little bit more. Or there's of course professional service jumpstart engagements that can assist with that sort of thing as well.
Great. Thanks, Gregory. RJ, what about which of the public event channels will GeoEvent Server product staff be available at?
So as Gregory was just mentioning, if you come over to the spatial analysis,
And
yes,
data
spatial
science,
analysis
yep.
and data science area in the expo, that's where it's not solely GeoEvent and ArcGIS Velocity, but there are a lot of big data and spatial analysis teams that are there, and that's where you'll find the GeoEvent team as well as ArcGIS Velocity.
Great, thanks, RJ. Another one for you, RJ. Can GeoEvent Server consume, process, and store raster data?
The quick answer to that is no. GeoEvent is processing data that can be organized in a data structure using Java primitive data types. So this value is a string, this value is a date, this value is a geometry. It can process video, and I thought I might have spotted a question on video standards.
That one's next.
There is a MSIB standard that I recall that is popular for video. So while GeoEvent's not going to be able to pull in the video frames, for example, as raster data is kind of a series of video frames, we could develop an inbound connector with a custom adapter that is able to pull metadata out of keyframes of the MSIB standard. It's not something that you're going to be able to do out of the box, but it is something we might be able to use the Java SDK to develop you might even need a custom transport. I'd have to talk with one of the developers more to see how to connect up to that MSIB standard and how to pull out the metadata.
So that kind of relates to this next question. What would a video standard format a security camera, what would a video standard format a security camera video to consume with GeoEvent? Essentially, what is the standard format that you could consume? Video format that you
and since
consume.
We don't pull in the video as raw data, there is no standard format that I could recommend. The question really comes down to how is the data being transmitted and how is the data being formatted. So we can adapt out of the box, for example, generic JSON, GeoJSON, generic XML. These are all self-describing standards. We can adapt delimited text. We can pull in the specific XML flavor from a GeoRSS stream, but we're not going to pull data from a video feed, for example. That's not something that GeoEvent will do out of the box.
Yep. Next question from Andrew. Does the difference creator processor permanently modify the geofence, or is the clip geofence stored in memory? I'll give that one to you again, RJ.
So all of the geometry processors have an option. You can either replace the event geometry or you can write to a new field that is of type geometry. Something that is probably key to understand with GeoEvent is that geometry is just another type of attribute. So a feature service can only have one type of geometry and only one geometry per feature record, whereas an event record could have multiple geometries and those geometries could be of different types. So you're never modifying the geofences. Those are a resource that are used to conduct your spatial analysis. What you're doing is modifying the geometry of the event record. So rather than asking about a geometric difference or a clipping operation, if I were using a different geometric processor like buffer, that's just going to create a polygon buffer about the event record and either write that into a new geometry field or replace the incoming, say, point geometry with the polygon.
Great, thanks, RJ. Gregory, one for you. When will 10.9 GeoEvent Server be released?
10.9 is slated for release, I believe the first week of May 6th through May 9th.
Great. RJ, another one from you from Erica. Can GeoEvent ingest or watch JSON CSV from OneDrive or other cloud data store locations?
I don't think so, Erica. I know that the watch a folder for files works with the system IO, the system file format. If you could map through a UNC path, you might be able to watch that as a folder, but No, I can't think of a way of connecting directly up to OneDrive.
Okay. One from Anonymous here. Will a service be able to be reused for multiple tokens? For example, if multiple accounts to a web service like marine traffic, then reuse the configuration in GeoEvent to process both tokens instead of maintain two identical services? RJ?
So the way that I'm going to try to answer that is that GeoEvent doesn't offer any sort of multi-step authentication or authorization. I can't, for example, make a request on a service given username, password, credentials to receive back some sort of authorizing token and then put that token into a second request that goes out to get the data. I have to build out my URL with all of my query parameters and be able to make a single request and get back a single response. So if you had some sort of long-lived tokens, you could pre-configure your multiple inputs, and then those inputs would just continue running using that authorization token. There wouldn't be any way outside of developing a custom transport to do any sort of automatic renewal when that token expired, for example. I hope that answered the question.
Thanks, RJ. Another one from Anonymous here. Can you please elaborate on how to define an input to use the Azure cloud?
So this kind of goes back to what I was saying about how the data is arriving, what format it is in, but it's really the other half of the question. That's how is the data being transported? GeoEvent supports data being posted over REST. It can query over REST. It can look at system files that are in system folders. But in terms of going out to the cloud, unless there was a URL and a RESTful endpoint that I could reach to query that data, that's not something GeoEvent's just going to connect up to, say, an Azure data lake, for example.
Yeah. Another one from Anonymous for you, Gregory. Any resources to share about integrating with other IoT platforms? Essentially, how do we integrate with IoT platforms?
Yeah, sure. So that kind of gets into some of the documentation that exists out there. I would invite you to check out the documentation on our various input connectors. That's going to go into the various inputs that are included out of the box, which a lot of them are pretty standardized to work with, a variety of different connectors. I think the key question here when it comes to answering that is, what's the format of the data and how is it ought to be brought in, because a lot of the time with GeoEvent, the out-of-the-box input connectors are capable of bringing that in. If you're interested in extending GeoEvent Server and looking into some more kind of third-party, data providers and how to bring that in, we do have our GeoEvent Server gallery, which has a bunch of components that can kind of extend the capabilities of GeoEvent. So that'd be another area to check out. But for more specifics, we're happy to talk about any sort of specifics, I should say, at the expo. If you'd like to join us there, can offer some more specific resources.
Great, thanks. So time for maybe one or two more questions here. Are there best practices for deploying highly available GeoEvent instances across multiple servers? RJ, do you want to take that one?
That is something we cannot cover here in a technical Q&A. Please schedule some time with us. There's a lot of material that I can share with you on that topic, but I'll have to defer that question.
Great, thank you.
Hey, Greg, I think
Greg, I
think you're
you
muted.
Thank you very much. Would you please share a use case that GeoEvent Server has been used in a smart city? RJ, can you think of an example of that where GeoEvent's been used?
I believe there were some big projects going on in the Middle East with the city of Dubai and also the United Arab Emirates, but I don't have any specific names. I'd have to go back to our professional services crew and find folks that were supporting those projects.
Great. Thank you very much for attending the session today. As always, feel free to visit us in the Spatial Analysis and Data Science event channel under Ask Our Experts, and we'll be able to answer any additional questions that you may have. So thanks again, and have a great rest of your conference. Thanks. Bye-bye.